All right, good morning, class. Here we are talking about Chapter 9, Cratered Worlds. So when we talk about cratered worlds, we're just talking about kind of massive things. So the most massive kind of cratered things where the surface doesn't get changed by weather or erosion or that sort of thing are going to be the Earth's moon and then Mercury. So we're going to start off with the moon. So here we have the moon. And the first thing you're going to notice about the moon is it's kind of got these two distinctive regions. It's got this dark region over here, which is kind of more recent lava flows that kind of resurfaced the moon early on in the formation of the moon and the solar system. And then you have this very heavily cratered area, which is kind of from the original formation of it, where it's just been pockmarked and hit by all kinds of things traveling through the solar system. Couple of statistics or data for the moon and Mercury. Notice that they're both fairly large objects, but still like 5% less of the mass of the Earth. Diameters fairly large, densities a bit more than water. Mercury is a bit denser than the moon, and we'll talk about that when we get to its formation. And then some other things that aren't terribly important. The moon is pretty cool because it is the closest astro body that we have. And we went there. We went there during what we call the Apollo program. So the Apollo program ran from 1968 to 1972. And it's when Neil Armstrong and Buzz Aldrin went to the moon 1969 and stepped foot on there, collected a bunch of samples and brought them back. There are a few other stops. Do we cover the stops on the moon here? Maybe that's part of the chapter that I left out. But there's a few other things that happened while we were there. We drove around in a moon buggy. We took some more samples, orbited the Earth a number of times, all during different stages of the Apollo program. Since then, we haven't been back to the moon in person, but we have sent a lot of things there. So from here, 1994 to 2020, you can see a large list of things, most of them orbiters that were mapping the moon, looking for water ice in the shadows and the poles of the moon, which they did find. There's quite a bit of ice there. Then there's one that was studying what the surface was made over. They called the impactor. So it crashed into the moon, and that was studied, the debris that was thrown up, and some other orbiters. And then there's kind of China doing some land roving on the moon and taking samples that way. The structure of the moon. You have the surface, which is pockmarked along with this kind of darker area, which is lava flows. And then there's this very, very thick mantle and a small core. Now, the mantle is pretty much just kind of silicates and rock, that kind of thing. Partially melted core, so not really fluid. And then a fluid outer core and a solid inner core. Again, that would be very much like Earth's. It's made up of nickel and iron. In our book, it says a depleted, or I think it says depleted core. That just means that the core is very, very small. It's there, it's made out of iron and nickel, but it's much smaller relative to the entire side of the moon than you would expect for a planetary body. Okay. So teeny tiny core, very, very large mantle, mostly solid. Okay. Impact craters. So the other great kind of defining structure on the moon are craters. They're just all over the place. One of the things you might notice is if you look closely at these craters is that they all appear fairly circular. So the reason for that is because when something runs into the moon, it hits it really, really hard, and that basically creates an explosive kind of outshooting of rock and material. That's illustrated kind of down here. Okay. We have craters on Earth, but they are basically from volcanoes. So here we have a picture of what a volcano crater, something we see on Earth, is. You get this mound built up from magma pushing the ground up, and then a little kind of divot in the top, kind of pushing it all out. Lunar craters are flatter, and they just kind of have a flat bottom, quite often with a little bump in the middle that you get from debris as it comes back down from the explosion. So what do we have here is the about that. A rock coming in from outer space, slamming at extreme velocities into the surface and causing a lot of things to heat up and explode outward. So you get all this debris flying up. You also get these shock waves that pass through the moon from the explosion. And it so happens that this causes circular indentations pretty much no matter which angle it kind of hits the surface at, because the distribution of the material isn't so much from the motion of the meteorite, it's from the explosion caused by the collision. So at this one explosion point, it kind of balloons out spherically, causing these more or less circular craters. Here's an example of one right here. Fairly circular, kind of round, some raised rubble in the middle. And then on the edge, you have some tiered formation that's just from material settling and then kind of falling down back into the crater. We can use this to estimate how old the moon is by just doing crater counts. Okay. So what do we do? Well, you can estimate the rate of cratering either by counting the number of things flying around in the solar system, or you can count the number of craters on the Maria. That's the melted part, the dark spot of the moon. And what you find is that you expect it to basically be kind of constant. So if you have a constant rate of impacts, then all you have to do is kind of count the number of impacts, and that gives you a time frame for how old that surface is. So what we see is that in the Maria, that is the melted portion, we see that mostly it's about 3.8 billion years old, that melted portion, the dark area of the moon. After that, you get into what we call the highlands, and that's the really cratered, really pockmarked areas of the moon. And you'll see, according to this graph over here, that the count goes way, way up. So kind of at that point, like that 3.8 billion years point. So what happened here? We have this region of time where we have what we call the heavy bombardment. So early in the solar system formation, there's a lot more things flying around, and things just got hit a lot more, leading to that really blanketed with craters area of the moon. Okay. Now, we can also verify this with the samples that we got from the moon. So if you take samples of the moon, you look at like carbon dating, radioactive dating. So you have elements in the crust and they're unstable. So you go like carbon 14 and it decays to carbon 12. Well, that happens at a predictable rate. And you can use that to calculate basically just how old that surface is. So according to those samples and the radiological dating, we get the same sort of numbers, that the Maria, the melted part, the dark part of the moon is about 3.8 billion years. And then the other heavily cratered part, that's about 4.2 billion years old, leading us to the near, well, the beginning of the solar system, really, that 4.2 billion years. All right. So how did we get a moon? Well, there's a few different theories that have been proposed in the past. One is the fusion theory. This picture over here illustrates the fusion theory. And the fusion theory is that basically, as it's forming the Earth is spinning, a little bit of the material comes off, and a little bit of material creates the moon, as it just kind of forms out of leftovers, much like the planets around the sun formed out of leftovers from the formation of the sun. We call that the fission theory. There's also the sister theory. The sister theory is that two independent kind of large blobs kind of formed together. So the moon and the Earth formed at the same time. And then there is the capture theory, that there was another moon-sized body moving around the solar system and during its creation, and that it got captured by Earth's gravity and couldn't get away. A number of problems with these. Number one, basically to capture something in the early solar system, it's going to be moving really fast, which would lead to an elliptical orbit, and our moon just doesn't have an elliptical orbit, so that doesn't really work out. And then there's all right, so where was I? Oh yeah, so fission theory, part of it somehow comes off, so that somehow means it's not a great theory. Sister theory, two things kind of formed together. The structure of the moon doesn't really support that. So if it was formed kind of in the same way, you'd expect a larger core relative to the mantle, and it doesn't have that. And the capture theory is improbable just based on the circular nature of its orbit, but also its composition. The best explanation we have is what we call the giant impact theory. So basically, you have two kind of large bodies, protoplanets in the early solar system, kind of in the same region, Earth's orbit. They collide. What happens is they collide is you get all this material out here thrown out from what was the mantle of the Earth. So at this point in Earth's history, it had differentiated somewhat, or probably kind of mostly, and all the heavier iron and nickel forms the core of the planet. And then you get all this debris, which is all the silicates and a bit lighter things, which accounts for the structure of the moon. So if you go back to the structure, the small core is a little bit of the kind of leftovers from the smaller of the impactors. And then you have this great big mantle from just kind of the surface material that was blown off the Earth and the other protoplanet when they slammed into each other. And that accounts for the similar compositions of the Earth and the Moon as far as silicates and just the elemental abundances of the mantles. Okay, so that's our best guess. The next one, Mercury. Mercury on the inside looks like this. You got a little bit of a crust, very pockmarked, lots of craters all over it. And then you got a thin mantle and this big, big iron core. Why is it a big iron core? Well, where it formed basically is an intensely radiative area that's hot, and the sun blows a lot of energetic particles out away from it at that point, and it blows off everything that's not super heavy. So a lot of silicates even that would make up, say, the mantle of Venus or Earth get blown into the outer reaches of the solar system, well, kind of back towards Venus and Earth, really. So you're left with just iron and nickel. The core of Mercury is a big iron nickel ball that's about the size of the moon. So a moon inside there, you know. Mercury has a rotation that is 59 days long. So it's not quite in lockstep with the sun, but it is pretty slow. How do we know that? Well, basically, we do this little trick right here. We have a radio signal, which we send out towards Mercury, and it bounces off of it. And when it comes back, the shape of the radio signal, how it looks when it comes back, will tell us about the rotation. And that's simply due to Doppler shift. If one side is going away and the other side is coming toward, then frequencies that are well, parts of the transmitted signal that are hitting kind of the right side versus left side of the planet will have a slight frequency shift. So if you look here and we see the signals, here we have a transmitted signal in blue, and return with no rotation looks exactly like original signal. If it's got a slow rotation, then it'll look pretty similar, but bulge just a little bit on the sides. And the faster it goes, you get more and more bulge. So we can do this, and we can then calculate how fast it rotates based on that radio signal. Turns out it rotates in every 59 days or so. The surface of Mercury looks a lot like the surface of the moon. So it's extremely marked, extremely pockmarked by craters. Notice they're all circular looking, again, because of that explosive nature of things hitting the surface. In addition to the pockmarked nature of Mercury's surface, it also has these long cracks that go through the surface. That you can see one of them here. And best guess for that is that after it had formed, it's still relatively hot in the inside, which causes it to expand a little. And it's getting bombarded, it's gotten bombarded. And after the bombardment, that heavy bombardment that we talked about earlier, it starts to cool. And when it cools, the surface differentiates a little bit. It cools at different rates, depending on, its position and how it's being illuminated by the sun. but that causes stress fractures that we see right here. And we know this happened after all this cratering because the fractures run right through those craters. That's basically it for this chapter. So there's a bit about the moon, a bit about Mercury, and there's some other interesting facts in there. But you should read it. And if you have any questions, you email me or stop by office hours, talk to me during class. All right. Have a good weekend. Talk to you later.